So in this lecture, we're going to start to construct molecular orbital energy diagrams. So if you recall from last time, we have our three types of molecular orbitals. And then what I could do is I could make a little table where I could have their relative energy. So the first molecular orbital type, MO, molecular orbital type. All right, sorry about that, but I don't know, MO, it's a helpful reminder. So we have the bonding molecular orbitals. And these have a low relative energy. We have anti-bonding. These are high energy molecular orbitals. Another way of thinking about the low is the low energy bonding molecular orbitals are stable, whereas the anti-bonding molecular orbitals are unstable. Now, with that in mind, we could consider the non-bonding molecular orbitals as being having sort of zero energy or mid-level energy, or really overall zero. And they define the 0 points on our graphs. Okay, so what I want to do is take these ideas into account and build a molecular orbital energy diagram for H2. So the molecular orbital energy diagram for H2 is going to look like this. We're going to have an orbital up here, which I'm just going to show as a line, and then an orbital down here. And these are our two orbitals. Okay, now I know they're not the shapes, but we can fit 2 electrons into these things. And so that's what I'm gonna do. I'm gonna put 2 electrons into this lower orbital. This lower orbital is going to be my bonding orbital. This other one is going to be my anti-bonding orbital. So what I've done is I've built a graph, and way over here to the left, I'm going to define the scale as energy. And the energy we're talking about is potential energy. So the y-axis is potential energy, and as you go higher up, you're going to get to higher energy things. In this case, we're looking at orbitals. You can think about this as the shelf, okay? We start by putting our electrons on the floor, and then the antibonding molecular orbital serves as a shelf, a higher potential energy system that we're not up to. Instead, what we start with are 2 atomic orbitals in the H2 molecules, or in the H2 atom, the H dot, the hydrogen radical atoms. They come together to make an H2 molecule. So we could consider the atomic molecular orbitals too. And I'm going to put 1 atomic molecular orbital on one side. So this is going to be the AO for H dot. And if it's got a dot, it's got an electron. So I'm just going to put that electron as this arrowhead here. Okay, that's an ugly arrowhead. So there is my electron. And it's an electron in an atomic orbital. And then these are the electrons after they've mixed together into a bonding molecular orbital. Now, if one H dot looks like this, the other H dot would have a similar height. I'm just going to draw it across the screen to the opposite side, and this is going to be the AO for our other H dot. Now this electron I'm going to have pointing down. This is called spin down. We also want our electrons to be spin paired. We don't have to worry so much about that. They seem to find a way to spin paired when they're forming bonds, but I like to just have them pointing in the appropriate direction before we do the before we form the molecular orbital. Then what we like to do is draw like little lines to connect the bonding molecular orbital, basically the molecular orbitals to the 2 atomic orbitals. So I have my 2 atomic orbitals on outside, and then it says that when these 2 mix together, we're going to form an equal number of orbitals, both molecular orbitals now. One is going to be a bonding molecular orbital, the other one's going to be anti-bonding. Now the thing about orbitals is they can all hold 2 electrons. So if we've got 2 electrons going into the system, we're going to put the 2 electrons into the bonding molecular orbital. So after the atomic orbitals and their 1 electron from H dot bond to form an H2 molecule, the following things happen. A bonding and antibonding MO form. Molecular orbital form, or an MO form. And the 2 electrons from each of the H dots occupy or exist in the bonding molecular orbital. Okay? Now, why do they occupy the bonding molecular orbital? Because the bonding MO is lower in energy. So if you think about it, and you're an electron, let's imagine you're an electron. An electron's kind of like a bowling ball. I know they're smaller than that, of course. The bowling ball, let's give the bowling ball a choice. Does it want to be on the shelf for its own good, or does it want to be on the floor? It probably wants to be on the floor because it's less likely of hurting itself or something else if it's up on the than it would be if it was up on the shelf. So we fill the lowest energy orbital first. We can put 2 electrons in. So that's a good note to make. Note that we still fill the orbitals from lowest energy first, and we can fill 2 electrons per orbital. It doesn't matter if it's atomic or molecular. Okay. Now, another subtle point to note is that the bond order can now be determined. After the MOs have been filled, the bond order can be determined. And this is helpful because we're trying to figure out what bonding looks like for these types of molecules. Now, I know this is just H2. We know what H2 does. It forms a single sigma bond, but we're trying to build on this and get into deeper things like conjugated pi systems, ultimately. So the bond order can be determined. And again, that is bonding electrons minus anti-bonding electrons divided by 2. Okay, so the bond order of H2 is 1. Because 2 minus 0 divided by 2 is 1. Okay, what this says is that HH will successfully form one bond between the 2 elements. Okay, and you're like, I already knew that. What am I doing that's new? Well, let's look at another example. Let's look at the He2 molecule. He2. Can this molecule form? There's a number of ways to approach answering this question. Molecular orbital theory can be one of those approaches. I'll just emphasize there are numerous approaches. Let's use molecular orbital theory to do this. Okay, so what we have here is an He molecule where the electrons in the He molecule are 2 and they both exist in the 1s atomic orbital. That's our AO. And what we're saying is, if we put on the left side and the right side, we're going to have 2 He's come together. Now, if you notice, in these atomic orbitals, I've added 2 arrows for having 2 electrons. That's because we're at He, we're not at hydrogen. Hydrogen was just a dot, it had 1 electron. He has a full version of its octet, that is 2 electrons. Its first shell is completely full. So we have 2 electrons in the 1s atomic orbital for He. It is full. In organic 1, we would say that's a stable molecule. So we don't need another bond to form. But let's use molecular orbital theory to also rationalize why we don't want to form a bond with, I like to make this nice and dark, between the 2 elements of H2. Now, if these come together, they would form 2 molecular orbitals because we started with 2 atomic orbitals. We would have a molecular orbital that's higher in energy. This is an anti-bonding molecular orbital. And then down below, we have a bonding molecular orbital. So we have anti-bonding and bonding. And what we can do is now fill up these orbitals with the electrons from our atomic system. So I'm going to put 2 electrons down below because we always start with the lowest energy orbital and add electrons until it's full. We fill up at 2. Okay, so we have 2 electrons. And now what are we going to do with the next 2 electrons? Well, we have to put them in the next orbital that's available, and that's the antibonding molecular orbital. So we have 2 electrons in the bonding orbital, encouraging bonding, and we have 2 electrons in the antibonding orbital, which we'll see discourage bonding. So now the bond order is 2 minus 2 divided by 2. That's equal to 0. That's saying that no stable covalent bonds will form. Okay, so we try to put He together to make He2. Our organic 1 system, our organic 1 mind is going to say, well, you can't do that because He's already got its octet. It's not going to want to bond again, right? Well, yeah, let's look at it a different way, and a way that's going to allow us to look at things more deeply, like pi systems and that sort of thing. And that's where we go to molecular orbital and we say, oh, okay, well, if I bring these 2 atoms together and the electrons in their atomic orbitals to try to make a sigma bond, I have a bonding and an anti-bonding orbital. And if you look, I've got 2 electrons in the bonding orbital and 2 electrons in the anti-bonding orbital. They cancel each other out. So what's happened here is, even though there are 2 electrons in a bonding orbital, and the bonding orbital encourages, and I'm going to call it a molecular orbital, even though the bonding molecular orbital encourages bonding, we still have two electrons in the anti-bonding orbital. Which discourage bonding. And if we discourage bonding, then we don't see bonds form, right? So these discourage bonds, and it turns out that the way this works is our bonding molecular orbitals, if we have 0 here, this is 0, our bonding molecular orbitals, I shouldn't have made that, I should have made this, all right, I'm going to just gonna make this a solid line. This is 0 energy. our bonding molecular orbital is lower in energy and it's more stable, but it's not as stable as the antibonding orbital is unstable. So this antibonding orbital is further from our zero line. So even though we have electrons that could offset the antibonding nature, the bonding discouraging nature of our antibonding orbital, those antibonding orbitals are still higher in energy. So even if there's a tie, that doesn't mean we're still going to see a productive interaction between those two atoms, according to molecular orbital theory. Instead, we say that, well, the antibonding orbital, if we have to put them way up there, that shelf is really high. It is not balanced effectively by the bowling ball being on the floor because that shelf is just so high. Anyway, the math works out. If there's zero, if the bond order is zero, we're not going to see a productive bonding, covalent bonding interaction between two elements. Okay. In the next lecture, we'll look at how to apply these things to pi systems, which is going to be helpful for understanding the reactivity going forward and try to make sense of some of the other systems we've looked at thus far. So anyway, that'll do it for this one.